Welcome to the deep dive. Today we are going on a deep dive into 100 years of math milestones.
Ooh, that sounds interesting.
It's this collection of math problems and stories from like the past century, all pulled from the Pi Mu Epsilon Journal.
Wow.
And it's packed with fascinating stuff.
I can imagine a whole century of math milestones.
So are you ready for some like mind-blowing math moments, maybe a newfound appreciation for math?
Absolutely. I'm always ready for more math.
Okay, well, the book actually started as like a special project for Pi Mu Epsilon Journal's centennial celebration.
Okay, yeah, that makes sense.
The editor, Stephen Miller, wanted to showcase a century's worth of mathematical progress.
Makes sense.
But, like, he had this dilemma.
Oh, what was that?
He thought that there wouldn't be enough, like, compelling problems to feature.
Really? Not enough interesting math problems. That's hard to believe.
Right.
Yeah, there's always more math problems to solve.
So that's where the collaboration comes in.
Okay, how so?
So Miller asked his colleagues for help and invited them to contribute problems.
Oh, that's a great idea.
Yeah, so this resulted in 4 centennial articles jam-packed with problems and reflections about math.
That's awesome. I love that collaborative approach.
Me too. So the book starts in 1915 with Einstein's theory of relativity.
Okay.
And right away, there's this centennial problem that asks us to derive Einstein's prediction for the bending of light
Interesting.
using the weak field approximation.
Okay, I'm intrigued. What's the weak field approximation?
So imagine space-time as like a warped rubber sheet, right?
Okay, I can picture that.
So a small object placed on that sheet would create a little dip,
Gotcha.
and that represents the weak gravitational field.
Okay.
So like if you rolled a marble across the sheet, it would be deflected a bit by the dip.
Ah, I see. So that simulates how light bends.
Exactly.
That's a really cool way to visualize it.
Yeah, and it lets us calculate the effects of gravity without like the full complexity of Einstein's equations.
Right. It's a simplified model that still captures the essence of the concept.
Yeah. So what's really cool about Einstein's theory is that it explains like existing observations that puzzled astronomers for like centuries,
Like what?
like the perihelion precession of Mercury,
Oh, wow.
but it also predicted new phenomena,
Oh, really? Such as?
like the bending of light around massive objects.
Yeah, I've heard of that.
Yeah, and that prediction was confirmed during a solar eclipse.
Wow, that must have been a huge moment for physics.
It was. And there's also this surprising discovery related to gravitational lensing.
Oh, tell me about that.
In 2008, researchers found that multiple point lenses can create a maximum of 5n5 images.
Wait, 5n minus 5? What does n represent?
Oh yeah, n is the number of lenses.
Oh, okay, I see. So with like 3 lenses, you could see 10 images of a single object.
Exactly. It's pretty mind-boggling.
It is. It's like the universe is playing tricks with our perception.
Totally. It's amazing how ongoing research reveals these new facets of theories like Einstein's relativity.
I know. It's like we keep peeling back layers of the cosmic onion and finding more and more to explore.
Okay, now let's zoom in to the world of numbers and talk about infinity.
Okay, always a fun topic.
Yeah, so in 1918, Georg Cantor revolutionized our understanding of infinity.
Yeah, he was a real pioneer in set theory.
He was. He introduced the concept of different sizes of infinity.
It's mind-blowing, isn't it, that there are different levels of infinity?
It is, like trying to list all the decimal numbers between 0 and 1. You could keep writing forever and you'll never capture them all.
Exactly. Because there are infinitely many.
Yeah. And to understand his argument, like imagine you have this list that claims to contain all real numbers.
Okay.
Cantor showed that you can always make a new real number that is not on that list.
So you can't ever have a complete list of all real numbers.
Exactly, proving that the set of real numbers is larger than the set of natural numbers.
It's like saying there's an infinity bigger than infinity.
Right.
Yeah. It's fascinating how he challenged our basic assumptions about infinity.
Yeah, it really changed our understanding of math.
Okay, so what's next on our math milestone adventure?
From the infinite to the, to the curves. Let's journey to the world of elliptic curves and Mordell's theorem in 1921.
Elliptic curves. Those sound a bit intimidating.
They sound it, but they're just plane curves defined by a specific type of cubic equation.
Oh, okay, so
Yeah.
not as scary as they sound.
Right. But they hold these secrets with applications in cryptography and number theory.
Interesting. So what does Mordell's theorem tell us about these curves?
Well, it states that the group of rational points on an elliptic curve is finitely generated.
Okay, break that down for me. What does that mean in simpler terms?
So picture a grid where each intersection is a rational number.
Okay, got it.
Mordell's theorem says that if you have an elliptic curve going through some of these points, you can generate all the other rational points on the curve just by using a finite set of building block points.
Ah, I see. So it's like having a blueprint for the rational points on the curve.
You got it. And you know what's even more amazing?
What's that?
Those applications. Elliptic curve cryptography is used to secure online transactions.
Oh, wow. So my online banking is safe thanks to elliptic curves.
Exactly.
That's pretty cool. I never realized how abstract mathematical concepts could have such practical uses.
It's amazing, right? Okay, so let's fast forward to 1924 when math kind of had this foundational crisis.
A crisis? What kind of crisis?
Well, mathematicians were grappling with the need for a solid and consistent basis for their work.
Oh, I see. It's like realizing the ground you're standing on might not be as stable as you thought.
That's a great way to put it. So they realized they needed a more rigorous foundation to avoid contradictions.
So what did they do?
They came up with the Zermelo-Hegel axioms.
What are those?
They're basically a set of rules for set theory, like building codes for the universe of math.
That makes sense. A way to make sure everything is logically sound.
Yeah, but even with these axioms, they still had a controversial element,
Oh, what was that?
the axiom of choice.
I've heard of that, but I'm not sure I fully understand it.
So it basically says that given any collection of non-empty sets, you can always choose one element from each set.
That sounds simple enough. What's so controversial about that?
It leads to some really counterintuitive results,
Really? Like what?
like the Banach-Tarski paradox.
Okay, that one always throws me for a loop.
It suggests that you can decompose a sphere into a finite number of pieces and then reassemble them into two identical spheres.
Yeah, that sounds more like magic than math.
I know, right? But that's the beauty of math. It can challenge our intuition.
True, it makes us rethink our assumptions about things we think we understand, like infinity.
Okay, now get ready for some unexpected patterns with Benford's law.
Benford's law, what's that about?
It's this law discovered in 1938 that says in many real-world data sets, the leading digit is more likely to be a 1 than a 9.
Really? That's so strange. Why would that be?
It follows a specific logarithmic distribution.
Interesting. So is it just a coincidence, or is there a mathematical reason for this?
There is. It stems from the concept of equidistribution.
Equidistribution.
Yeah. It basically means the fractional parts of logarithms of numbers tend to be uniformly distributed.
That's a bit over my head.
Well, the point is there's a deeper mathematical reason for why this pattern emerges.
Okay, I'll take your word for it, but it's still a very strange and unexpected pattern.
I know, right? And the craziest thing is this law can be used to detect fraud.
Really? How so?
Well, if someone is like making up numbers, they're less likely to follow Benford's law.
Oh, I see. So it's a way to check if the numbers are too perfect to be true.
Exactly. It's a pretty powerful tool.
That's fascinating. Math really can be used in unexpected ways.
Okay, so now for a fun story. In 1940, George Dantzig accidentally solved two unsolved problems in statistics.
Wait, he accidentally solved them. How is that even possible?
He thought they were just homework assignments.
Wow. Talk about a lucky break.
Right, and these weren't just any problems, they were significant challenges in statistics.
So he basically stumbled upon solutions while doing his homework.
Yeah, and his solutions had a big impact on the field.
That's incredible. It shows that sometimes a fresh perspective can make all the difference.
Totally. Okay, so moving on to John von Neumann,
Ugh.
a legend in the world of mathematics.
He was a polymath who made like groundbreaking contributions to lots of fields.
Yeah, I know, game theory, economics, computer science, the list goes on. What does he do in 1944?
He did work on game theory, particularly the concept of Nash equilibrium.
Right, the idea that in a competitive situation, there's a point where no one can improve their outcome by changing their strategy alone.
Yeah, like imagine a chess game.
Ugh.
Each player's trying to win. But Nash equilibrium is that point where both players are making their best moves based on what the other player's doing.
So it's like a stalemate, but where everyone is playing their best.
Exactly. And von Neumann's work emphasized how important it is for math solutions to be unique, especially when modeling real-world stuff.
Why is that?
Well, if a model is supposed to predict the future, having multiple possible solutions creates uncertainty.
That makes sense. If you have 5 different paths to choose from, how do you know which one is the right one?
Right, and that's what von Neumann was grappling with, the importance of finding unique solutions to problems. Okay, so uniqueness is key. What's next?
Okay, how about a math problem that's like about matchmaking?
Matchmaking. Sounds intriguing.
It's called the stable marriage problem in 1962.
Okay, what's that all about?
So it asks how to pair like men and women based on their preferences so that no two individuals would want to switch partners after the matching is done.
Sounds like a tricky problem.
It is, but there's an algorithm for that,
Really? What is it?
the Gale-Shapley algorithm.
And that guarantees a stable matching.
It does, and it has applications beyond matchmaking,
Like what?
like assigning students to schools or doctors to hospitals.
Wow, that's pretty versatile.
Yeah.
So math is helping to make the world a more organized and efficient place.
It is. Okay, now hold on, because we are about to enter the world of secret codes.
Ooh, I love a good code-breaking story.
In 1977, there was a breakthrough in cryptography with the development of public key cryptography.
Oh, yeah, I've heard of that. But how does it actually work?
So imagine trying to send a secret message without having to share a secret key beforehand.
That seems impossible.
Well, public key cryptography makes it possible.
Oh.
So you have this public key that anyone can use to encrypt a message,
Okay.
but only the person with the private key can decrypt it.
Ah, I see. So it's like a lock that anyone can close, but only you have the key to open it?
Exactly. And the coolest thing is that the security of this relies on the difficulty of factoring large numbers into primes.
So number theory is at the heart of internet security. That's mind-blowing.
It is. And just think about all the things we rely on secure communication for.
Online banking, email, shopping, the list goes on. It's really incredible how public key cryptography has shaped the digital age.
Okay, so from secret codes, let's move to brain teasers.
Sounds like a fun change of pace.
Sudoku became really popular in the 1980s.
I love Sudoku. But what's the math behind it?
Well, one interesting question is, what's the minimum number of clues needed for a unique solution?
That's a good question. Too few clues and you have multiple solutions, but too many and it's too easy.
Yeah, and this simple question leads to really complex math in complexity theory and combinatorial design.
So there's a lot more to Sudoku than meets the eye.
Definitely. And for our final stop, we're tackling the Kepler conjecture from 1998.
Oh yeah, the sphere packing problem. How to fit the most spheres into a given space.
Exactly. Kepler thought that the face-centered cubic lattice was the densest packing.
Like how oranges are stacked in a grocery store?
Yes. And it took centuries to prove his conjecture.
Really? Centuries?
Yep, it was finally proven in 1998 by Thomas Hales.
Wow, that's a long time to wait for a proof.
I know. And the proof involved a lot of computer assistance.
So computers are playing a bigger role in math these days.
They are, and it's changing how we approach some of these really complex problems.
That's really interesting. It makes you wonder what other mathematical mysteries are out there waiting to be solved with the help of computers.
I know, right? There's still so much more to explore. We've covered so much in this first part of our deep dive.
I know. It's incredible how much ground we've covered. I can't wait to see what other mathematical gems we uncover in the next part.
Me too. Stay tuned.
Welcome back to our deep dive into 100 years of math milestones.
I'm ready for more.
Okay, well, in this part, we're going to move from like the historical stuff and look at more recent developments in math.
Sound good.
So like, how about we start with Project Euler?
Project Euler, what's that?
It's this website that launched in 2001, and it's like, it's a collection of challenging math problems.
Oh, okay.
But they are designed to test your math thinking and also your programming skills.
So it's like coding and math all in one.
Exactly. So you get a problem, and then you got to write a program that computes the solution.
Huh. That sounds pretty challenging.
It is, but it's also really satisfying when you crack a tough problem.
I bet.
And there's this whole online community where you can talk about solutions and strategies.
Oh, wow. So it's like a social thing, too.
It is, and it shows how math can be accessible to anyone with an internet connection.
I like that.
Me too. So speaking of powerful tools for math, how about we talk about Sage Math?
Sage Math.
Yeah, it's this free and open source software for math.
Oh, cool.
Yeah, and it can do like everything.
Like what?
Algebra, calculus, number theory, cryptography, you name it.
Wow, that's a lot.
It is, and it's all thanks to collaborative development and the open source movement.
So it's like having all these powerful math tools at your fingertips.
You got it.
That's awesome.
Yeah.
Okay, so how about we go back and revisit some of those earlier milestones, but like go deeper into the math?
Sounds like a plan.
Okay, so we talked about Einstein's theory of relativity, but what about that absolute differential calculus?
Yes, the mathematical framework that underpins general relativity.
Can you explain it like I'm 5?
Okay, so imagine you're trying to describe the geometry of like a curved surface, like a sphere.
Okay, I can picture that.
The absolute differential calculus gives you the tools to do that precisely.
So it's like a language for curved surfaces.
Exactly. And it let Einstein describe gravity as the curvature of spacetime.
Wow, that's pretty mind-blowing.
It is.
And the book has this centennial problem about calculating the volume of a sphere with a cylinder cut out.
Oh, yeah, that one sounds tricky.
It is,
Yeah.
but it shows you this cool problem-solving trick.
Oh, what's that?
If a problem is really hard in its general form, try simplifying it and solving it for like a specific case. It's like breaking down a big puzzle into smaller pieces.
Right. And once you solve the simpler case, you might see how to generalize the solution.
Makes sense. Okay, so what about Cantor's work on infinity?
Well, besides that diagonalization argument, he also introduced the concept of p-adic numbers.
P-adic numbers, those sound a bit abstract.
They are, but they give you this different way to measure distances and define convergence.
I'm not sure I follow.
So imagine a number line, but the distances are all distorted.
Okay, I'm trying to picture it.
It's like looking at the world through a funhouse mirror.
Okay, so things that are normally close together might be far apart in this p-adic world.
You got it. And the book has this problem that asks you to visualize how integers sit within this p-adic number system.
That sounds like a challenge.
It is, but it's a good exercise for your mathematical imagination.
Okay, so let's go back to Mordell's theorem and elliptic curves.
Sure.
The book has this problem that asks you to prove something about the rank of an elliptic curve.
Oh, yeah. The rank is a key concept for understanding the structure of elliptic curves.
Can you explain it a bit more?
So the rank basically tells you how many independent infinite families of rational points exist on the curve.
Okay, that makes sense.
The problem asks you to prove that if an elliptic curve has infinitely many rational points, then the rank must be positive.
So it's about connecting the number of points to this concept of rank.
Right. And it gets into the nitty-gritty of the algebraic structure of elliptic curves.
Okay, so from infinity to axioms, what about the axiom of choice?
Well, there's a problem in the book that asks you to prove that the power set of a set is always larger than the set itself.
Hold on, power set, what's that?
It's the set of all possible subsets of a set.
Oh.
So like if you have a set with 3 elements, its power set has 8 elements.
Okay, that makes sense.
Okay.
So what does this have to do with the axiom of choice?
The proof relies on the axiom of choice, and it shows that there are different levels of infinity.
Different levels.
Yeah, like the power set of a set is always a bigger infinity than the set itself.
Whoa, that's mind-blowing.
I know, it challenges our intuition about what infinity really means.
Totally. Okay, so now let's revisit Benford's law.
Oh yeah, the law of leading digits.
So the book challenges readers to explore the connection between Benford's law and this.
It is. It shows how different areas of math can be connected in surprising ways.
Okay, so let's go back to George Dantzig and his accidental solutions.
Ah, yes, the story of the mistaken homework.
So the book dives into the context of those problems and how they relate to hypothesis testing.
Hypothesis testing is a fundamental part of statistics.
Can you give an example?
Sure, like imagine you want to test whether a new drug is effective.
Okay.
You would collect data from a group of people who took the drug and a group who didn't.
Gotcha.
And then you would use hypothesis testing to see if there's a statistically significant difference between the two groups.
So it's about drawing conclusions from data.
Exactly. And the problems that Dantzig solved were about developing new methods for hypothesis testing.
Cool. Okay, so how about we play a game?
A game?
Yeah, the book talks about this game called Hex.
Hex? I've never heard of it.
It was invented in 1942, and it's played on a hexagonal grid.
Okay, sounds interesting.
Yeah, and it's impossible for the game to end in a draw.
Really? How do they know that?
They proved it using topology.
Topology, that's a study of shapes, right?
Yeah, and it can be applied to game theory, too.
Wow, math really is everywhere.
Okay, now let's talk about code breaking during World War II.
I love those stories.
So the book talks about how mathematicians at Bletchley Park cracked the Enigma code.
Yeah, Alan Turing and his team.
They were amazing. They figured out how to break the German military's encryption.
Yeah, it was a major turning point in the war.
It was, and it also had a big impact on the development of computers.
Right, because they had to build these machines to help them crack the code.
Okay, so now for something really mind-bending. The Banach-Tarski paradox.
Ah, yes, the one where you can duplicate a sphere.
How is that even possible?
Well, it's a mathematical theorem, and it relies on the axiom of choice.
Okay, remind me what that is again.
It basically says that given any collection of sets, you can pick one element from each set.
Right.
And using that axiom, you can prove that you can decompose a sphere into a finite number of pieces and then reassemble them into two identical spheres.
But that doesn't make sense. How can you get more volume from the same amount of material?
It's because the pieces you break the sphere into are really weird. They're called non-measurable sets.
Non-measurable.
Yeah, it means you can't really assign them a volume in the usual way.
Okay. My brain is hurting.
Yeah, it's a really counterintuitive result, but it shows how math can lead to these surprising and mind-boggling conclusions.
Okay, so how about something a bit more down to earth?
Yeah.
What about the QR algorithm?
Oh, that's a classic algorithm in numerical analysis.
What does it do?
It finds the eigenvalues and eigenvectors of matrices.
Eigenvalues, eigenvectors. Remind me what those are.
So an eigenvector of a matrix is a vector that when you multiply the matrix by that vector, it just scales the vector.
Okay.
Then the eigenvalue is the scaling factor.
Ah, okay. So why are these important?
They tell you a lot about the behavior of linear systems.
And linear systems are everywhere.
They are. In physics, engineering, economics, you name it.
Cool. So the QR algorithm is like a tool for analyzing these systems.
Exactly. It's a really efficient way to find those eigenvalues and eigenvectors.
Awesome. Okay, so for our final stop, how about the unreasonable effectiveness of math?
Ah, yes. Eugene Wigner's famous observation.
Could you explain what he meant by that?
So he was amazed by how well math describes the physical world.
Like how?
Well, think about Newton's laws of motion.
Okay.
They're expressed in mathematical equations, and they predict the movement of objects with incredible accuracy.
That's true.
And it's not just physics, it's the same in chemistry, biology, even economics.
So math is like the language of the universe.
You could say that. Wigner believed that there's this deep connection between math and reality.
That's a really profound idea.
It is. It makes you wonder why math is so effective at describing the world around us.
Wow, this has been an incredible journey through the world of math.
It has. We've covered so much ground, from ancient problems to modern algorithms and everything in between.
I'm really starting to appreciate the power and beauty of math.
Me too. There's always something new to learn and explore.
Welcome back to our final part of this deep dive into 100 years of math milestones.
Yeah, it's been quite a journey.
I know. We've seen so much, like from set theory to cryptography.
Yeah, and now we're in the 21st century where math is becoming even more powerful with computers and all this collaboration.
Totally. So how about we start with Project Euler again?
Okay, yeah, it's a great example of how math is becoming more accessible to everyone.
Right. Like anyone can go on that website and try to solve those challenging problems.
Yeah, and it's not just about finding the answer, it's about the thinking process and the coding skills you develop along the way.
Yeah, and there's that whole community aspect too.
Right, people helping each other out, sharing ideas.
I love that.
Oh.
Okay, and what about Sage Math?
Oh, Sage Math is like a game changer for mathematicians.
It is like having a super powerful math lab on your computer.
Yeah, and it's all free and open source.
It's easy.
Yeah.
And the book encourages readers to actually use Sage Math.
It does. Like there's this centennial problem. There's basically a call to action to go explore Sage Math.
I like that. Okay, so now let's go back in time to 1913 and talk about Paul Erdős.
Ah, Paul Erdős, a true legend in the world of math.
He sounds like a really interesting character.
He was. He was like this wandering mathematician traveling the world, collaborating with everyone.
Wow, he must have known like every mathematician.
He pretty much did. He co-authored over 1,500 papers.
1,500. That's incredible.
I know. He was obsessed with solving problems, especially in number theory and combinatorics.
And he was known for offering cash prizes for solutions.
He did. He was like a one-man math competition.
I love that. Okay, so from Erdős, how about we jump to 1914 and talk about Martin Gardner?
Ah, Martin Gardner, the master of mathematical puzzles.
Yeah, he had that mathematical games column in Scientific American.
It was so popular. He had this way of making math fun and accessible for everyone.
He did. He introduced millions of people to the joys of math.
It's like he opened up this whole new world of mathematical thinking for so many people.
I wish I had read his column back then. Okay, so let's go back to 1915 and revisit the weak field approximation.
Sure, it's a really useful technique for simplifying those complex equations of general relativity.
Yeah, it makes it easier to calculate things like gravitational lensing.
Right. And without it, we wouldn't be able to study those fascinating phenomena in astrophysics.
Okay, so how about we play another game?
Another game.
Yeah, this one's called Hex.
Hex.
It's a two-player strategy game played on a hexagonal grid.
Oh, okay. I've never played that one.
One cool thing about Hex is that it can never end in a draw.
Really? How do they know that?
It's been proven mathematically using topology.
Wow, that's pretty neat. It's like there's this hidden mathematical guarantee that someone will always win.
Yeah, it makes the game even more interesting. Okay, now for a real-life spy story.
Ooh, I'm
The
intrigued.
breaking of the Enigma code during World War II.
Ah, yes, a classic tale of code breaking and mathematical ingenuity.
So mathematicians at Bletchley Park figured out how to crack the German military's secret code.
Yeah, Alan Turing was one of the key figures in that effort.
He was. They developed these amazing algorithms and built machines to help them decipher the messages.
It was a huge breakthrough, and it played a crucial role in the Allied victory.
It did. And it also had a big impact on the development of computer science.
Absolutely. Okay, so how about we go back to the Banach-Tarski paradox?
Oh yeah, the one that still makes my head spin.
It's a mind-boggling result, isn't it? The idea that you can duplicate a sphere by cutting it into pieces and reassembling them.
Yeah, it just doesn't seem possible. Like you're creating something out of nothing.
It's not really about creating something from nothing. It's more about the strange behavior of infinite sets and non-measurable sets.
Okay, I'm still trying to wrap my head around that one.
It takes some time to get used to those counterintuitive ideas, but it shows how math can push the limits of our understanding.
Okay, so how about something a bit more practical?
Yeah.
What about the QR algorithm?
Ah, the QR algorithm. It's a workhorse in numerical analysis and linear algebra.
Can you remind me what it does?
So it's used to find the eigenvalues and eigenvectors of a matrix.
Right, those tell you a lot about how a linear system behaves.
Exactly. And the QR algorithm is really efficient at finding those eigenvalues and eigenvectors.
So it's used in a lot of different fields.
Oh, yeah. Physics, engineering, computer science, you name it.
Okay, so for our final stop, how about the unreasonable effectiveness of math?
That's a great one to end on. Eugene Wigner was really onto something with that observation.
Yeah, it's amazing how well math describes the world around us.
Like, think about the laws of physics. They're all expressed in mathematical equations.
And they work. Like we can use those equations to predict how things will move or how much energy something has.
Exactly. It's like math is the language of the universe.
And it's not just physics, it's chemistry, biology, even economics.
Right. Math is everywhere. It's this powerful tool for understanding how things work.
Wow, this deep dive into 100 years of math milestones has been incredible.
It has. We've covered so much ground, from ancient problems to modern algorithms.
I've learned so much about the history of math and the amazing people who have shaped this field.
Me too. And it's clear that math is more important than ever.
It is. With all the challenges we face in the world, like climate change and disease.
Yeah, we need math to help us find solutions.
We do. So keep exploring, keep questioning, and keep marveling at the wonders of math.
That's right. The journey of discovery never ends.
That's it for our deep dive into 100 years of math milestones.
Thanks for joining us.
We hope you've enjoyed the exploration and are inspired to continue your own mathematical adventures.
Until next time, keep those mathematical minds engaged.